it's wonderful that we have as our first plenary speaker, Melanie Matchett Wood. Melanie is famous throughout the mathematical world, partly because she was famous very young, but has continued to develop more and more recognition. She is a faculty professor at Harvard. Many other institutions have had the benefit of Melanie's presence over the years. She has received many honors. For example, most recently, in 2025, she was made a member of the National Academy of Sciences, but also she received the Presidential Earlier Career Award. She's a member of the American Academy of Sciences, author of the MacArthur Fellowship, and the list goes on and on. So we have here a very distinguished mathematician who gives excellent talks. And we will hear her excellent talk. Her research is motivated by questions in number theory, but she also studies arithmetic and algebraic geometry, probability, and random groups. And that's why the title of her talk, which I don't actually have written down, but you all have on your app, the title of her talk is not number theory, but involves all sorts of other types of mathematics which she will bring together for our edification and enjoyment. Thank you, Melanie.
Good morning. All right. Yes, so it is lovely to be here in Miami, and to be here with all of you to talk about some mathematics, and for us all to enjoy this week of mathematical adventures together. So what I'm going to talk about, as you see on my title there, is an application of probability theory for groups to three-dimensional manifolds. So as Susan said in her introduction, this work was actually motivated by questions in number theory, and maybe I'll make a brief gesture towards that, but what you will see in the title is probability theory, algebra, topology, and all of those things arise, and the kinds of investigations that we have done in all of these areas inspired by some questions in number theory. And what I talk about today is all joint work with Will Sawin. Okay, so the question that we're going to pursue is a question about three-dimensional manifolds. Okay, so just so we're all on the same page, a three-dimensional manifold is a topological space that locally looks just like the three-dimensional reals that we're used to. So if you were walking around in this space, just you look around, it looks what you're used to. And in particular, just to be precise, today my three-dimensional manifolds are all going to be orientable, compact, without boundary, and three-dimensional manifolds. And so what are some of these spaces? So they have to be compact. So that doesn't include R3, for example. But one that you could make is the three-dimensional torus. So we start, it's hard for me to draw the three-dimensional torus, but I can draw S1, the circle. And if I take the circle across the circle, I get the torus, the surface of that donut. That's a two-dimensional manifold. And if I took that donut and I cross it with S1, the torus, two-dimensional torus cross S1, so think about sort of taking that around in a circle, except we can't really embed it in this three-dimensional space that we're living in. I get a nice example of an orientable compact three-dimensional manifold. I could also take a different compact two-dimensional manifold, like the two-sphere, so the surface of the three-dimensional ball, that's a two-dimensional compact manifold, and I could cross that with a circle. So take that, cross the circle, you get another nice three-dimensional manifold. Or something that is a lot like R3 is the 3-sphere, so that's, if you like to imagine the 4-dimensional ball, that's the boundary of the 4-dimensional ball, but also a 1-point compactification of R3. So it's like the space that's just like our, a 3-dimensional R3, but with 1 point that out at infinity that you go to no matter which direction you headed. Okay, so those are some examples of the kind of 3-dimensional manifolds I'm going to be talking about today. And the property of them that I'm interested in is their fundamental group. So this is like the first algebraic invariant we define for topological spaces to try to understand one topological space from another and get a sense of the paths, the ways around the space. So the fundamental group pi1 of M, the group of base loops in M up to homotopy under concatenation. So on that 2-dimensional manifold there, you see this, the torus, the surface. There, you can see 2 loops in red and blue that are, they're technically different as paths on the surface, but up to homotopy, they're the same because you can slide one over to the other. And those paths up to sliding one to the other are the elements of the fundamental group, and because you can follow one loop around and then follow another, you have that concatenation of paths that makes this a group. And so in these examples, let's say what the fundamental groups are. In our first example, the 3 torus, S1 cross S1 cross S1, the fundamental group is Z cubed, the free abelian group on 3 generators. And the next example, S2 itself has trivial fundamental group because if you make any loop on the boundary of the 3-dimensional ball on the 2-sphere there, you can always shrink it down to a point. But when you cross it with S1, you get one way to travel around in a loop. So the fundamental group of S2 cross S1 is Z. And then the fundamental group of the 3-sphere is trivial. So I write 1 there for the trivial group. That's a little abusive notation. But so those are some examples of 3-dimensional manifolds and their fundamental groups. So for short, we'll often call these 3-manifold groups, meaning the fundamental groups of 3-dimensional manifolds. And the question that is going to motivate the work that I'm talking about this morning is, what finite groups can be quotients of these 3-manifold groups? In what combinations? And I'm going to spell that out a lot more, but just to get you oriented, that's what I'm going to be asking about. And so besides the fact that if you just want to understand groups, you might want to think about their finite quotients. The finite quotients of the fundamental group have a particular meaning topologically because by the correspondence between covering spaces and the fundamental group, the finite quotients of fundamental groups are exactly the deck transformation groups of finite covering spaces. So this is also asking a question about what kinds of finite covering spaces can 3-dimensional manifolds have. And I'll also say that for me, since we heard Susan's teaser that this is motivated by questions in number theory, so for me, I'm motivated by the analogy between these fundamental groups and Galois groups of number fields and these, if you have a big profinite Galois group, say absolute Galois group of a number field or something like that, the finite quotients that correspond to finite Galois groups, finite extensions, and so that's where I get this eye of trying to understand a group through its finite quotients. Okay, so I like examples, so there will be lots of examples, so we'll do some more examples, and then I will make that question, that sort of vague question about what finite quotients can we have, more precise. Okay, so here is another kind of more interesting way to make a compact 3-dimensional manifold. I'm going to start with 2 copies of a genus G handle body So that is a solid three-dimensional object. So now these pictures are not referring to just the surface there, the two-dimensional thing, but like the whole three-dimensional donut you might take a bite out of. Here the genus pictured is 3, but you could imagine sort of adding more holes. If you had G holes, you get the genus G handle body. But these themselves are not three-dimensional manifolds in my sense because they have the boundary. You know, when you're inside of them, they look like a three-dimensional manifold, but you hit a wall. If you're like a little ant crawling around inside, you hit the wall, and it's no longer a, at the boundary there, a three-dimensional manifold. But we are going to repair that, and we can do that by gluing the two handle bodies together along their boundary. So inside one of the handle bodies, topologically, when you get to the boundary, it's like you have a half space and there's a big wall. Well, and the other handle body, there's also a half space and a wall, and we can mathematically identify those walls and then get, as we glue it together, a compact three-dimensional manifold without boundaries, so the kind that I am talking about today. And so it's sort of like you imagine if you were the ant crawling around inside of this donut. Whenever you hit the surface, there's a magical portal that zips you over to the exact spot on the other donut, but now you're crawling in instead of out. So that makes a compact three-dimensional manifold. And the fundamental group of this three-dimensional manifold is more interesting maybe than the groups we saw before. It's the free group on G generators. And it's not hard to see what those G generators are because they're sort of G, here G is 3, sort of 3 ways around to go around these holes in the handle body. And those get identified between the two handle bodies when you glue them together, and so the whole fundamental group turns out to just be a free group on G generators. That in particular implies that every finite group, G, is a quotient of some three-manifold group, because of course every finite group is the quotient of the free group on G generators for G sufficiently large. So in my last slide, when I had that question that said, well, what finite groups can be quotients of three-manifold groups and in what combinations? The reason that I added that in what combinations, the reason that's the interesting question is because maybe the first question you would ask, which is what finite groups can be quotients of three-manifold groups at all, what finite groups can be deck transformation groups of finite covering space maps of three manifolds is answered beautifully and easily by this one nice construction of a three-manifold, which exhibits, as you range over G, the number of holes in your handle body will exhibit all possible finite groups as quotients of three-manifold groups. Yes, the question. Yes. Yes.
Is it here an abelian or
no? Yeah, great question. So this free group, is it abelian or non-abelian? This is the non-abelian free group on G generators. So yeah, on the last slide I mentioned we had the free abelian group, the Z3, but this is the non-abelian free group on G generators. So you have, some elements, you call them x1, x2 up to xg, and you have essentially words in those elements and their inverses to make up this free non-abelian group. So that's why it gets, that's the reason I said, it's more interesting than the examples, because there's a lot more that happens with this non-abelian group, and that's what lets you get every finite group, not just the finite abelian groups as quotients. All right, so I'm going to do another example, kind of similar to this last one, but to build another cool three-dimensional manifold, compact without a boundary, and that is the Poincare homology sphere. So there's a lot of different ways you could construct the Poincare homology sphere, but this is the one I really like. So, okay, instead of starting with the handle body, We're going to start with a dodecahedron as pictured here. So a solid dodecahedron, but when we start out, it has this two-dimensional boundary, sort of like the handle body did. But I'm not going to take 2 copies. I'm only going to take 1 copy, and I'm going to identify the boundary of this dodecahedron with itself in various ways. So I'm going to take each face of the 12 faces of this dodecahedron, and I'm going to identify it with the opposite face. So each face has an opposite face. You're looking at sort of like a front face and a back face. But one has to think a little bit to think exactly how you're going to identify them. Because if you look straight through, there's not like a natural identity map. Because if we look at, for example, in the dodecahedron here, that front face has, it's a top vertex. And behind it, there's no top vertex. It's rotated a little. So we have to be careful to make some consistent choice of rotations. And when we do that, we glue all of the boundary of the dodecahedron to the opposite faces with a precise rotation telling us how to do that. We get a compact 3-manifold without boundaries. So now it's like you're an ant inside of this dodecahedron, and when you hit a wall, you get a little dizzy as it kind of spins you a little bit and transports you to the other side of the dodecahedron, and you'll be facing back in. Okay, so this is an example of the Poincare homology sphere, and its fundamental group is actually a nice, interesting non-abelian group of order 120. The maybe easiest way to say what it is its SL2F5, so the 2x2 determinant 1 matrices over the Z mod 5Z, or the finite field with 5 elements. But that's a little bit of just a coincidence of these smallish groups where there's lots of different ways you can describe them. But one nice reason to describe it that way is because then one can see that it does not have very many finite quotients. It's not quite a finite simple group, but PSL2F5, where you take SL2F5 and you take the quotient by diagonal matrices, you see that that's kind of famously on the list of finite simple groups, and so it's not going to have any other interesting quotients besides the trivial group. So we see, as opposed to the last example, where we had a 3-manifold group that has lots and lots of finite quotients, every finite quotient under the sun that can be generated by G elements. This is an example of a finite but non-trivial 3-manifold group, fundamental group of a 3-manifold, but that only has a few finite quotients. All right, and so now I will make that question from the last slide more precise when I said, well, what finite groups can be quotients of 3-manifold groups and in what combinations? I can ask here, given finite groups G and H, is there a 3-manifold where the fundamental group, the 3-manifold group there, has G as a quotient but not H? So I said this is a question. It's really like a question sub GH. For every finite group G and finite group H, we can ask the question, is there a 3-manifold that has G as a quotient but not H? And in fact, you can, you can have maybe several groups that you want as quotients and several that you want to avoid as quotients. I'm going to just focus on 1 and 1, but in the work that we do, you can have sort of arbitrarily many, finitely many groups that you want to ask, are these quotients? Well, these are not quotients simultaneously. So we need a single fundamental group that has G as a quotient, but not H. All right. So like I said, this is actually many different questions, one for each G and H. And so I'll give some answers. We'll start with some quite obvious answers and move on to things that are a little more subtle. So here is a silly way in which the answer can be no. If H itself is a quotient of G, I guess that's all there was to say there. It was that silly. The answer has to be no. Obviously, if H is a quotient of G, then no, there is no three-manifold with G as a quotient but not H, because if you have G as a quotient, you have H. So, it's not like, oh, the answer is always yes, but it's also not that the answer is always no. There are many easy ways to give yes answers. There as a three-manifold that has G as a quotient but not H. So for example, if I take that group of order 120, SL2F5 that I just had, that's the fundamental group of the Poincare homology sphere. That is a fundamental group of a three-dimensional manifold. And now I just take H to be some bigger group. I just picked GL2F5 because that's a bigger group than SL2F5, but you could take any finite group that's not one of those three quotients on the last slide, and you can say, yes, there does exist such a three-manifold that has G as a quotient but not H because I have exhibited it. The Poincare homology sphere is an example. So whenever you have an example of a three-manifold explicitly that you know its fundamental group, you'll get a bunch of yeses. Let me emphasize that the no here, this silly no, this is not for a topological reason. There are certainly groups that have G as a quotient but not H for any two finite groups. So that's just a, sorry, what do I want to say? Sorry, the no is not for a topological reason. It's only for a group theoretic reason, which is that there are no groups that have G as a quotient but not H, if H is a quotient of G. So there's nothing to be said. There's no topology that enters the silly no, and there is some topology that enters the easy yeses because they come about from us exhibiting actual topological three-dimensional manifolds. So now, let me give some less obvious answers. So these answers, again, examples. I told you I love examples, so a lot of this is in examples. These are some examples of answers that follow from this joint work with Will Sawin. So here's a no. All right, I'm going to build a group here as a semi-direct product. The group is F3 squared, so F3, that's the finite field of three elements, or you could call it Z mod 3. So F3 squared, semi-direct product SL2F3. And so F3 squared is like length 2 vectors over F3, and SL2F3 acts exactly how you would expect matrices to act on vectors, just by matrix vector multiplication, and that makes a semi-direct product. So that's an example of a finite group. And the statement here that I hope is not obvious, I don't think it's obvious, but it is true, and we prove it, is if that group is a quotient of your three-manifold group, pi1 of m for some three-manifold, then H, now I'm going to give you a different group. This is a larger group. This group has F3 squared, so you could think of that as 2 by 2 matrices over F3, semi-direct SL2F3. So again, SL2F3 acts in the way you would expect a 2 by 2 matrix to act on another one by matrix multiplication. So that's a bigger group because we put in like an extra copy of F3 squared there. And I'm saying that this H is also a quotient of pi1 of m. So that, in contrast to the silly no, that is a fact of topology, not a fact of group theory. Certainly, there are plenty of groups that have this G as a quotient but not H, like that group G in particular has G as a quotient but does not have this bigger group H as a quotient. So there's nothing group theoretically that says if G is a quotient of your group, H has to be a quotient of your group. But it is a topological fact about three manifolds that we show. Yes, question?
Relevant in that claim?
Is the 3 relevant? That is a good question. Not especially. There are many other very similar examples where you can replace 3 with other primes. Yeah. Yes. Yeah. Just like, matrix multiplication is like multiplication separately on each column as a vector. That's, exactly that operation. So this is saying something. I mean, you can think about it topologically. It's like if you have some kind of covering space of your 3-manifold, you must have a bigger one. Or for this 3-manifold group, you have some quotient. There's something about 3-manifold topology that makes you have a bigger quotient. All right. And now I'll give an example of a yes. So here is another, this is another group of order 120. And here I've written it as Z mod 3 cross Z mod 5. And then semi-direct Q8. So Q8 is the quaternion group of order 8. And the quaternion group, you can take 2 different homomorphisms to the group of order 2, i.e. if you just think of those as plus or minus 1. And then you can use one of those homomorphisms to act on Z mod 3Z by multiplication by plus or minus 1, and one to act on Z mod 5Z by multiplication by plus or minus 1. So that gives you an action of the quaternion group, and you can build a semi-direct product like that. And also, this is just the first of a family of examples. The quaternion group actually has 3 non-trivial homomorphisms to the group of order 2, and so there's a notion of what's called a generalized quaternion group, where there's actually 3 cyclic groups it's acting on. Here, secretly, there's like a Z mod 1 and a Z mod 3 and a Z mod 5. And you can similarly change the 1, 3, 5 to many other numbers and get other examples of generalized quaternion groups. And this is just the first one. And here, actually, I'll give you a lot of yes examples. So for each n, in fact, there is a 3-manifold where its fundamental group has this G, this group of order 120, as a quotient. But it has no other quotients of order up to n. So maybe n is a trillion. And I'm saying there is a 3-manifold group that has G as a quotient, but no other quotients of order up to a trillion. Now, why did I have to put no other quotients in quotes? Of course, if G itself has some quotients like the quaternion group, the group of order 2, those obviously will appear as quotients. So when I say no other quotients, I mean except those quotients of G itself. Now, this would not be impressive if I told you this yes for the Poincare homology sphere. That was a different group of order 120, because we know a 3-manifold group that has that G as its fundamental group. So of course, if G itself in this last example here were the fundamental group of a 3-manifold, then you would not be surprised, that it would be automatic that for every n there is a 3-manifold, that one, that has G as a quotient, but not any other quotients of order up to a trillion. But it is, in fact, a very deep fact, only following from Perlman's work on geometrization, including the proof of Thurston's elliptization conjecture, that allows us to know that that particular G is not ever itself the fundamental group of a 3-manifold. So what this tells you is that when I promise you that there is a 3-manifold that has this group of order 120 as a quotient, but no other quotients, finite quotients of order up to a trillion, it actually has some bigger finite quotients. All right, maybe, of order 2 trillion. And so then when I promise you, there's a 3-manifold that has this G as a quotient, but no finite quotients of up to order 2 trillion, that has to be a different 3-manifold. So there are, in fact, infinitely many 3-manifolds whose, in the appropriate topology on the space of groups, whose fundamental groups approach this group of order 120, but never quite get there. And they approach it in an interesting sense. It's kind of like a p-adic flavored topology, where, as you get closer and closer to the group, this group itself, you'll have some finite quotients that are very, very large. And then you get closer and you have only even larger finite quotients besides this one. All right, so that is a sort of family and a style of yes examples where we say indeed there are three manifolds that have G as a quotient, but not H, so there's lots of H's in here, lots of examples. And this, again, is also just the first in a sort of natural infinite series of examples. And in fact, there is, like I said, this is a question for every G and every H. And in our work, we give a theorem that gives not just some yeses and some nos, but it gives always either a yes or a no. So a full answer, and that has to be phrased in some way, because obviously, as you see, there are sometimes yeses and sometimes nos, and there are some sort of subtle things going on. So we have to organize the answer in some way. And one nice way to organize the answer to understand where the yeses are and where the nos is in this topology that I was just sort of briefly referring to. So we put a topology on the set of groups. So this may be, if this isn't a level of, a way in which we may often be operating. We might think of a group, and then you put a topology on the group, and you have a topological group, like a Lie group. No, this is a topology on the set of groups. So the points in the space are the groups. And so a basic open in this topology is the set of groups with G as a quotient, but not H, for each finite group G and H. And so why did I put that topology on? Because that topology is exactly the topology that is relevant to this question. And so I'm going to say something in this topology, and that will be, it will be exactly what one needs to settle this question. I'm going to describe the closure of the set of three manifold groups in this topology. So in particular, to understand the closure of a group in any basic, open, if that basic open intersects the closure, then there must have been a point in the original set. And so this tells you for every basic open, based on a G and an H, if there was actually a three manifold whose fundamental group was in that basic open that had G as a quotient but not H. All right, and now I'm not going to get into the technical. Yes.
What are the isolated points of this topology?
The isolated points of this topology. Well, on the space of. Yeah, so by an isolated point, you mean a point that is open and closed? Well, if you allow, if we're not saying anything about yet three manifolds, and we're just talking about groups in this topology, I don't believe that there are going to be isolated points. So, yeah, good question. All right. This is a basis for the topology. Now this topology, okay, if we're going to be, if you really want to be clear, so this topology morally is really just a topology on profinite groups. It does not distinguish between two groups that have the exact same set of finite quotients. So for our purposes, that's fine because we're only asking about finite quotients. Of course, if you're interested in, there are plenty of other kinds of interesting groups that don't have have a lot of finite quotients, it's not really interesting to study this topology on them. But for the kind of groups that we're interested in, for example, 3 manifold groups are usually what's called residually finite, which means any 2 different elements are distinct in some finite quotient. They have very rich finite quotients. This is a good topology to understand some features of the 3 manifold groups. But of course, on some kinds of groups that don't have finite quotients, it's a very silly topology. Yes?
Yes, stupid question. So, the connected components have to do with certain manifolds, or how do they associate?
In this space of groups? Yeah, so so this is just, so far we haven't said anything about topology. It's just about a space of groups. And if you want to sort of try to picture this space, the easiest way to start, or the first example to have in mind is like the p-adic numbers. So that's this sort of totally disconnected topology where you say 2 numbers, they are close if they agree mod 3, and they're even closer if they agree mod 9, and they're even closer if they agree mod 27. And so sort of all of the 3-adic integers are in one of 3 balls for the residues mod 3, and inside of those there's sort of 3 balls for each of the residues mod 9 that agree with that residue mod 3. And so that's the flavor of this topology. It does not look like itself a manifold. It has this p-adic style topology. All right. So okay. So I'm going to put up our description of the closure of the set of 3 manifold groups in this topology, and I'll say a little bit about some of the conditions. But what I want to say is that, first of all, this is an exact description of the closure. So what that means is that these 4 conditions give you all the yeses and all the nos. So either the 4 conditions give you a reason, an obstacle, and say, no, there is not a 3 manifold with G as a quotient but not H, or or if nothing arises from these 4 conditions that eliminates that possibility, then we promise that, yes, there is a 3 manifold that has G as a quotient, but not H. Now, let me just say something about the language of what this answer is in terms of. So it's in terms of representations of groups over finite fields, and the group cohomology of the finite groups. Okay, so what you really need to understand about a finite group G and H in order to determine whether there's a yes or a no is their group cohomology. Now, I mean, obviously, since we saw there were some yeses and some nos, there was going to have to be something about the group theory of G and H that entered the question, and what it turns out to be here is group cohomology with coefficients in various representations, so with twisted coefficients, or you could think of them as local system coefficients. And we don't have to, I just want to give you a flavor of the sense of the kind of statement and what's involved. We're not going to go into all the technical details, but I'll tell you that of these 4 conditions, the first 2 are the ones that are really interesting and new in our work. For example, the first condition, which is some parity condition on some dimension. Whatever it is, it tells you that some dimension of some H1 cohomology group is even. That first condition there, that is what is responsible for that non-trivial no that I mentioned to you. That F3 squared semi-direct SL2 F3, if that was a quotient, then you needed to have a bigger quotient. That comes because of this parity condition. And you can just sort of work out as an exercise in finite group cohomology, that if that is something you want to do an exercise in, that this first condition here implies that no that I gave you on the last slide about F3 squared semi-direct SL2 F3. The third and fourth conditions are both follow from Poincare duality on the three-dimensional manifold, so they're group theoretically, they're very classical, but we just have to list everything that's true, whether it's new to our work or not, because like I said, this is an exact description that gives sort of all the no's and all the yeses. And the first two conditions are quite parallel. They're just about, one is sort of odd characteristic and one is even characteristic, and they're both just parity conditions on some group cohomology. All right, so what does proving such a theorem entail? Yes? Yes? Oh, there may be, sorry, that G should have been a capital pi. I think I was trying to, for some reason, yes, thank you, that's a great point. In these last two, the capital G should be the capital pi. That was a mistake in my slides. I was sort of changing the letters and I missed those. Thank you. Okay, so what does proving such a theorem entail? So first of all, we need to show that 1 through 4 are true about pi 1 of m. 3 and 4, I told you, sort of follow from Poincare duality. And for 1 through 4, for 1 and 2, we use traditional tools of algebraic topology. We make some arguments with cobordism. New work, but the kinds of approaches I will say, are traditional in algebraic topology. But then the other part of that theorem is that for any finite groups G and H, if those conditions 1 through 4 don't prevent a group from having G as a quotient but not H, then we need to prove that there is an actual 3 manifold with G as a quotient but not H. And for this, we use a probabilistic method. So this is not such a traditional method in studying these 3 manifold groups in this way, to use a probabilistic method to produce examples. So that means when I told you, yes, that there were 3 manifold groups with certain G as a quotient but not H, like that generalized quaternion group, I don't actually know how to write one down. I cannot write you down an example, but I can prove it exists because I use a probabilistic method and show that in a certain model it occurs with positive probability. So it must be there somewhere. Okay, and what is that probabilistic model? So we actually use already a way of building a random 3 manifold that is due to Dunfield-Thurston from 2006, which is the model of a random Haggard splitting. So before, remember, I took those 2 handle bodies and I made you a 3 manifold by identifying their boundaries along the identity map. It turns out there's a lot of different ways you can identify a surface of genus G with a surface of genus G, and those are in fact parameterized by something called the mapping class group. It tells you a lot of different ways you could have identified the surfaces besides the identity. And so Dunfield-Thurston suggested taking a random element of the mapping class group to identify the surfaces of the 2 genus G handle bodies in a random way. How you do that is not so important, but for example, there are lots of well-known generators of the mapping class group, and you could take a random word in those generators of length up to L, and you could take L to infinity. So that's sort of one way to think about getting out there randomly in the mapping class group. And then, and this is important, one doesn't do this for a fixed G, but lets G go to infinity. Because it turns out that even though this might seem at first like a special construction, all 3 manifolds, these compact-oriented ones that we're talking about today, occur this way for sufficiently large genus, where that genus, that means sufficiently large, depends on the manifold itself. But in any case, then morally, as we let G go to infinity, we're actually seeing all of the 3 manifolds via this random construction, not just a few special ones. So this is a way, this is a natural way to, if you want to try to think of just taking a random 3 manifold from this kind of compact orientable ones. I think maybe the nicest way to do that just to begin with, because it sort of spreads out and let you see all the 3-dimensional manifolds. And you can see that in this limit, you get any particular 3-dimensional manifold, for example, with probability 0. So even though a single 3-dimensional manifold could be produced in multiple ways via Haggard splittings, there aren't any that are somehow accumulating too much mass of this probability distribution. And so what we actually do in our work is not just answer this question about G's and H's, but we actually find the distribution of the pro-finite completion of the fundamental group of such a random 3 manifold. So, okay, so a couple things. This pro-finite completion, if that is, in this case, equivalent to just saying we know exactly you can think of the pro-finite completion as knowing exactly which finite groups are and are not quotients of the group. So it is exactly the information about the finite quotients of the group, which this whole talk has just been about what finite quotients do you have. And we find with precise formulas the distribution of that as a probability distribution for this random variable of this random 3 manifold. All right, so what does that even mean? So we are familiar with, usually when we think about probability distributions, often probability distributions of numbers. There are many well-known distributions of numbers, like the Poisson distribution, which is a natural distribution on the natural numbers, or the Gaussian or normal distribution on real numbers. And some of those distributions, like the Poisson distribution, we describe by giving exact formulas, like the probability you hit this K is something. Wait, did I put in that formula? I maybe didn't put in the formula. But that's how we describe the Poisson distribution. And others, like a Gaussian distribution, we don't describe the normal distribution by pointing at specific values and identifying their probabilities, because they're all 0. But we instead describe by giving probabilities that the value from the distribution lands in a particular open, in a particular interval, right? That's how we describe something like the normal distribution. And so similarly, when we have probability distributions of groups, sometimes we're an example like the Poisson distribution. So there's a beautiful probability distribution on finite abelian groups that was introduced by Cohen and Linstra in their heuristics about class groups of quadratic number fields, in this case real quadratic number fields. And this is a probability distribution on finite abelian groups that says you have a random finite abelian group I'm calling XCL, and the probability that it is a particular finite abelian group A is, the numerator is just a number. It's a product over zeta inverse values, where zeta is just the Riemann zeta function, and it's over the size of A and the size of the automorphism group of A. And this has formulas that where you specify the probabilities one by one, like a Poisson distribution, but actually this has universality like the normal distribution. So I'll just briefly mention that this is a result of mine with Hoi Nguyen from 2021, that if you take a random n by n plus 1 integral matrix, where you take the entries independent and identically distributed from basically any distribution that isn't sort of trivially degenerate, then for a fixed finite abelian group, the limiting probability that if you build a group from that matrix by taking its co-kernel, or equivalently its column space, or equivalently in generators and n+1 relations given by the n+1 columns of the matrix. You make a random group from that random matrix, and it will be in this Cohen-Lenstra distribution. And so the universality there is that you build a random matrix, and you get to pick whatever you want for the entries of your matrix, from your craziest, weirdest distribution you can think of. And just like the central limit theorem tells you, if you have your craziest, weirdest distribution you can think of, and you take the appropriately normalized averages of IID copies of that, you'll get the Gaussian distribution. Similarly here, if you take the craziest, weirdest distribution you think of, and you build a random abelian group in this way, you still get this universal Cohen-Lenstra distribution. Okay, so that's one kind of probability distribution on groups. I'll just mention here what I meant by non-degenerate is it should not be constant mod p for any prime p. That's a sort of obvious necessary condition. But some probability distributions on groups, and the kind that is relevant here in this 3-manifolds example, are such that the probability in your distribution that a random group is isomorphic to any particular group is 0. So you can't describe it by saying, okay, here's your probability, here's your probability. You have to give probabilities on opens. And I'm going to give an example of a kind of open, which is an open set in the topology that I mentioned before, where the formulas are particularly nice. I mean, you might, I'm going to put up a formula, you may disagree, but so, okay, if we have a word in formal variables, let's say like A, B, A inverse, B inverse, we'll call it universally trivial in G if it's the identity whenever the variables are replaced by elements from G. So for example, that word A, B, A inverse, A, B is universally trivial in a group exactly if the group is abelian. The commutators are all trivial when a group is abelian. And so if we let G and H be finite groups, for a group H, I'm letting X, GH be the quotient of X by all evaluations in X of all the words that are universally trivial in G and H. So what that says is kind of all the structural things that are sort of universally true about the groups G and H. I look at the maximal quotient of X where those things still hold. So that turns out to be an open set in this topology. So for example, the word A to the order of G, order of H, that's trivial for every evaluation of A as an element of G or H. And so that would have to be also trivial in XGH. And so, yeah, so as I mentioned, so this, okay, what is open then in this topology that I mentioned before is the set of all groups such that this GH quotient XGH is some particular F. And from these quotients, you can answer this question of whether G and H in particular are quotients of X. So it's very well suited for this sort of question that I asked. And so I'm going to put up like a big formula, but really it is not that bad. And I'm going to just give one sort of case of what it looks like. And this is, so I'm now taking these Dunfield-Thurston random groups where I glued the two genus G handle bodies together. And I'm asking what is the probability that this GH quotient, this quotient that really only cares about like things that are true in G and H of the fundamental group is some F. And we get a formula in terms of, here this is the group homology of F. And then we get a finite sum of products that express explicitly this probability in terms, again, of the finite group theory of F. And so these are products over minimal, non-trivial group extensions of this group, so all in terms of this group theory of this finite group F. And one thing I really want to point out, the main important feature of this expression, and here I said this is sort of one case, so there are cases of some different things, but in this case, this expression is explicitly positive. All right, so we have whatever it is, it's explicitly positive. So you have, a positive orders of things, and then you have a bunch of products of terms. And so as complicated as it may look, when you get such an explicitly positive formula, you know that there must be some three manifolds that have this, say, F as the GH quotient. And it is this shape of formula and this positivity that allows us to prove our yes answers and exhibit, well, not exhibit isn't the right word, prove that there are three manifolds that have G as a finite quotient, but not H, whenever, indeed, that is not obstructed by one of our topological conditions on three manifold groups. All right, and I will end there. Thank you. Yes.
I'm curious, what is the motivation from number theory to?
Yeah, so what is the motivation from number theory? That's a great question. So there is this beautiful analogy between number fields and three manifolds. And in this analogy, the class groups of number fields, so one of the most sort of recognizable invariants of number fields, they are analogous to the H1s, the homology of the three manifold. So that's the abelianization of the fundamental group. So in this beautiful analogy between number fields and three manifolds, the question about the distribution of the class groups of number fields is exactly analogous to the question of the distribution of the abelianization of these three manifold groups. So this example that I mentioned from this Cohen-Leinster distribution, which they were thinking about with distributions of class groups of real quadratic fields, is not unrelated to the three manifold thing. In fact, it's very closely related. And so number fields, they are like three manifolds because their cohomology has a three-dimensional duality called the Artin-Verdier duality. And so that in our sort of quest to understand class groups and their non-abelian generalizations, the Galois groups of unramified extensions of number fields, we came to wanting to understand this analogous question for three manifolds. Okay. Yes.
Why Taiwan of three manifolds and not surfaces? Is there like a...
Oh yeah, okay, that's a great question. So why three manifolds? So three manifolds is like the interesting thing. So that we understand, in fact, the classification of compact orientable surfaces quite well. They all are just like those surfaces of the handle bodies, and we know exactly what their fundamental groups are, and it's very explicit. So in 2 dimensions, certainly in 1 dimension, very well understood sort of simple behavior. In 4 and higher dimensions, you can get any finitely presented group as a fundamental group, so sort of everything is possible. So there's sort of no topological restriction. And then, as many things are like this in the dimensions, at 3 dimensions, at the 3-dimensional manifolds, there's enough complexity that, you saw, like, there are really non-trivial things going on in what groups can appear and what can't, but yet it's not, it's sort of rich And the answer isn't simple in either direction. So that's somehow, as many things in topology, right there around 3 dimensions is where a lot of the really beautiful complexity is. Yes?
And a curiosity kind of question, like you say for the yes answer, with this probability you can say that they do exist, but like, can you like, is it conceivable that you can like have kind of flows starting from these constructions which lead to some like concrete kind of example? Or
Yeah, so that's a beautiful question of whether, with these probability distributions, that there are some kind of flows that lead to concrete examples. That's a great question, and I don't yet have a good answer, but I think there are many exciting things to explore about these probability distributions, including questions like that, and also questions about universality, like the example I mentioned related, in the spirit of the central limit theorem.
So, can you give some intuition about why this probability is positive?
Why it is positive? How we prove prove that that's the probability. Some question of how we prove. Yeah, so how we prove that is the probability. That comes from recent work that we have done on the moment problem for probability distributions on groups or more general algebraic kinds of structures. And what that allows us to do is just like in traditional probability distributions on numbers, where you might recognize a distribution from its moments. We show that there's a notion of moments for things like random groups, and that you can recognize distributions from those moments. But moreover, and this was what was critical in this work, is that if all you had were the moments and you didn't know a distribution from those moments, you can do a kind of inversion process and construct those formulas like what you saw there for the probability explicitly from explicitly from moments in such a way that you can detect whether the probabilities are positive. So I didn't get to talk about that, but the whole side of how we get those probabilities, most of the new work there is in our work on the moment problem for random groups and other kinds of algebraic objects.